Welcome to the resonance. Get set up. Okay, this is resonance structures. Resonance. In chapter 1, we are going to be introducing some very, very important concepts, little vocabulary, resonance structures equals forms equals contributors. We'll use these three words interchangeably. These are better representations than a single Lewis structure. So back to Lewis structures. Let's give an example of something with a 2- charge, just to illustrate the point. We'll generally be looking at things with negative and positive, but that's not a big deal. This 2- charge is real. And if you were to come up with a Lewis structure and count electrons and start placing your atoms, you might come up with something like this. Two oxygens have a formal charge, one oxygen is neutral. And that would be correct as a Lewis structure, but it would not exactly represent this carbonate. This is called a carbonate dianion. It wouldn't perfectly, or it would be less than perfect representation. So let's look at this again. Let's draw that one again. We're going to push electrons. So a few things I'll say verbally. Resonance structures are multiple Lewis structures with the same placement of atoms. That's very important. Okay, same placement of atoms, but different placement of electrons. Resonance is only movement of electrons. It's really very, very important. Another word we're going to introduce is called delocalization, as opposed to localization. As opposed to a charge being localized on one atom, or two atoms in this case, it's going to be delocalized over multiple atoms. The more spread out, the more stable something is. And that's going to become very important when we talk about acid-base chemistry and things like that. So here we can push electrons in, put our electrons back on oxygen there, and push these electrons up. You need to have double bonds, essentially, double or triple bonds to really draw resonance structures. So we'll use this arrow to indicate, a double-headed arrow to indicate resonance. Notice that through this resonance form now we've moved the negative charge onto a different oxygen. Let's draw another one. These electrons can push in and push these back to that oxygen. All right, that was a mistake. Single bond there. Let me redraw that, okay? Get to see me make mistakes from time to time. Okay. There we go. You'll find that you'll be writing these things very quickly. So now these two charges are shared on these two oxygens. So shared, that's where the negatives are. Here's the negatives, and there's the negatives. So the take home is this oxygen negative charge is spread out. Okay, this is not equilibrium. That's really important. We'll see equilibrium arrows soon enough. They're different. But it is, and it's not going back and forth. So we'll talk about this again. I'll repeat myself a lot in this lecture. It's not going back and forth. Okay. Let's draw a hybrid of these three structures. So there's A, B, and C. Again, these are resonance forms, contributors, or structures. All three of these are a partial representation of the actual anion. Let's draw the hybrid, meaning it's just a mixture. It's a mixture of all three. That's all we mean. A mixture of all three resonance forms. So let's draw that. And the way you draw a hybrid, there's a carbon there, is you put in all the electrons that aren't moving. Each oxygen has 2 pairs of electrons. Each carbon-oxygen single bond is not changing. It's only the double bonds that are changing. And you can put sort of dashed lines to indicate that it's a sharing of those, what we're going to call pi electrons, these double bond electrons. We have a partial negative. That is a Greek letter delta, and we're going to use that to represent partial. Partial negative, partial negative, partial negative. You actually have you have 2/3 of a negative charge on each oxygen. That adds up to 2, the 2 minus. Okay, that's the hybrid. So again, these 3 structures help us to understand the hybrid. We'll use resonance structures a lot more than we use hybrids. We'll have to draw a few hybrids. Same atom arrangement, different electron arrangement. Extremely important. Okay. So let's go over some rules, or rather, let's make a list of what resonance structures are not. Let's start with that. Resonance structures are not the following. They're not real. Only hybrid exists. Okay, the carbonate anion is a single thing. Okay, they are not equilibrium. We'll use that to abbreviate equilibrium from time to time. They're not equilibrium. Electrons are not actually moving back and forth. They are the hybrid. Okay, I want to emphasize that so that we understand. We're using a convention to understand something. So no interconversion. Let's use that word. They are not interconverting between each other. And they're not isomers. We introduced isomers briefly. We'll see a lot of isomers. And isomers are different arrangements of atoms. Only the electrons differ here. Okay. So that's some things about resonance. Let's give you a few rules. Let's do this on the next page. Rules. Number 1. Only multiple bonds or really electrons change. Again, not atoms and not single bonds. Number 2, they must be valid Lewis structures. We'll talk about what we mean by that. We'll show some invalid structures. They got to be valid Lewis structures. This is a preference. I'm going to say filled octets preferred. It's a preference, and it helps us understand some things about reactivity, but it's not an absolute. Okay, there's exceptions to this, but filled octets are preferred. Lastly, less important, but still important, same number of what are called unpaired electrons. It's called a radical. Okay. Less important, initially at least. We'll see a lot of pairs of electrons mostly, but the same number of unpaired electrons. You can't just break apart all your double bonds and make a bunch of radicals. Okay. So a word about arrows. Okay. There's a lot of arrows that we'll be using. Some are reaction arrows, some are equilibrium arrows, some are resonance arrows. When we talk about electrons moving, we're going to try to communicate that. Electron movement. there are two possibilities, and one is going to be overwhelmingly used. Okay, when you have a, let's just put an atom, doesn't matter what it is, with a pair of electrons on it, atom A. Okay, some atom. These electrons can do things. We're going to show a regular arrow. Arrows, electron movement arrows always start at the electrons, meaning the arrowhead is the end of those electrons. So you don't want to flip this arrow around. This means something. It's very important. It means two electrons have moved, or they're not leaving the atom, okay, but the atom is using those electrons to form a bond or something like that, okay? Double bond electrons can also move, okay? So X, Y, doubly bonded, this can happen, okay? We'll see a lot of this. A single electron can move by the following. You got an atom with one electron. This is called a radical, and we use what's called a Fishhook arrow. A Fishhook arrow means one electron has moved, okay? So that's just a word about arrows that's really important. And let's go over some examples. All of these things, the lists and the words don't help, okay? So we need to go over some examples. So let's start. You can have a plus charge, you can have a pair of electrons with a minus charge, etc. So let's give some examples. This one we'll see quite often. It's called a carboxylate. It comes from a carboxylic acid. You have a minus charge on one oxygen. One of these pairs of electrons can come down, form a carbon-oxygen double bond, push these electrons up. The resonance form that we would draw with this looks very similar. But now the oxygens have changed their charge. Okay, so down here we have a negative charge on that oxygen. Over here we have a negative charge. Again, formal charge is assigned to an atom, and it's formal. It's bookkeeping. The reality is, let's draw a hybrid for this. The reality is that charge is, there's a half of a negative charge on each oxygen. So let's draw the hybrid. This is a hybrid that you may have to draw. Draw all the bonds that have not changed and the electrons that have not changed, two pairs on each. And then what do we have? This pair of electrons here that I'm sort of not circling with ink but swirling around here is now, let's circle that actually. There's that circled electron pair is that. I'm pointing to it now. It's become a double bond. This double bond is now pushed up here and has become a pair of electrons, okay? So that means there are, in a sense, a half of a double bond between the carbon and each oxygen. That's how we draw that, a dashed line. There's a delta negative, which means partial, partial negative, half of a negative charge, excuse me, on each oxygen. That is the hybrid. Let's do another example. Do what's called a carbocation. These bond angles will become, this is the right way to draw it. You'll understand this soon enough. Again, chapter 1, and we have to kind of get through the whole chapter for things to make sense. But there's a plus charge on this carbon. This plus charge, think of plus charges as wanting electrons. Okay, we're going to see it's going to play out a little differently with oxygen and nitrogen compared to carbon, but electrons want to go toward it, which means we can draw this moving over. Electrons can't just fly off an atom; they can't move over 4 atoms, but they can go to they can flow to an adjacent carbon to make another carbon-carbon bond. Okay, again, they're not moving back and forth, but we would draw a resonance form that looks like this. Now the carbon-carbon double bond is on the right in this representation. These two resonance structures are equivalent or equal in energy, let's say. And the hybrid, let's put H, the hybrid looks like this. Let's put in all the atoms that have not changed. Again, no atoms are moving around, only electrons. In this case, we don't have a lone pair. We have just a double bond that is being shared. 3 carbons are sharing 2 electrons. What do we have? Delta, but now it's a plus. Delta plus. There's a half of a plus charge on each carbon. Okay, let's do another anion. So now we have an anion, and I'm going to finish this structure, but just look at that. Carbon with 3 bonds and 2 electrons. If you calculated the formal charge, you get negative. It's on the carbon. Here, we're going to put an adjacent set of atoms. And now we have a double bond there, carbon-oxygen double bond. So this pair of electrons can donate in. Again, the hybrid will draw that. The carbon pair of electrons can push in, form a carbon-carbon bond. That forces, this forces those electrons to go up to oxygen. You can only have 4 bonds to carbon. You cannot have 5 bonds. As you form a 4th bond to carbon, those electrons have to go up to oxygen. Again, I can't say this enough. It's not going back and forth, but that is the language that we tend to use. The carbon-carbon bond is shown in this form, or contributor. I like the word contributor because they're both contributing. I'm going to abbreviate the CH3 there. We'll see that a lot too. So now we have 2 resonance contributors. And let's draw a hybrid. Draw in all the atoms, all the unchanging pairs of electrons. Now, what is changing? A lone pair is becoming a double bond, and a double bond is becoming a lone pair, so to speak. We have a shared charge, but now, again, we're back to delta minus. So it's either going to be delta plus or delta minus. There is delta minus, meaning partial minus on the oxygen, partial minus on the carbon. Now, a look ahead to electronegativity, a very, very important concept. Here, we would use language of minor and major. There's a major contributor and a minor. We'll use this terminology. There are better and worse resonance forms or contributors. The major is the major because oxygen is more electronegative than carbon. I just want to kind of plant this in your mind now. It's more electronegative, therefore it's the major resonance contributor. Okay, so we might say this has 60 to 70% of the charge, and this has 30 to 40% of the charge. Okay, that's just a look ahead. We'll get to that a little bit later. Let's do another anion though, and this one's going to be equivalent. Got another carbanion, we call it. That looks very similar to how we started last time, but now we're going to put a carbon-carbon double bond next to it, kind of like the carbocation we did two slides ago. Same idea, electrons push in, these push over, you get a resonance form. Put in all our atoms. Let's draw the hybrid. All the atoms that have not changed. And now we have a pair of electrons, 2 pairs of electrons that are shared amongst 3 carbons. And we have a delta minus, delta minus. We would say these 2 resonance forms A and B are equivalent now. Because there's a minus charge on 2 carbons, it's 50% on each. All right. Let's talk about, let's do some more examples, but let's talk about valid versus significant. Use a couple terms here. Valid versus significant. Okay. So I'm going to show 4 resonance forms. This molecule here is acetone. And a lot of single bonds, and we got a carbon-oxygen double bond with 2 pairs of electrons on oxygen. Again, a glimpse about electronegativity. There is more electron density on the oxygen because of the electronegativity. We'll talk about that in the next chapter. But let's draw a resonance form that is invalid. Let's say those, I'm not going to draw the arrow because I'm going to draw several things. Let's say the electrons push down. I'll kind of show the arrow here. Pushing down to form a carbon-carbon triple bond. So now we're left with 1 lone pair on, I'm going to abbreviate these CH3s. Again, you'll see this soon enough. And we have a negative charge on the carbon and a positive charge on the oxygen if you calculated those formal charges. The big problem with carbon there is you have 10 electrons around carbon. It's violating this so-called octet rule. There simply are not the orbitals to be able to fill that many electrons around carbon. So it's invalid. It's not allowed. Okay, it's a Texas carbon. It's got 5 bonds. 5 bonds to carbon is a big no-no. Now let's draw another one that is valid but insignificant. Let's push the electrons down onto carbon. This double bond is going to push electrons onto carbon. Let's show that one. 2 lone pairs still on oxygen, but now we're going to have a plus charge on oxygen and a valid carbanion with an oxygen plus. Okay, this is valid but insignificant. Okay, it's insignificant because oxygen's more electronegative than carbon. Electrons are going to flow toward atoms of electronegativity, with higher electronegativity. Now let's show one that is valid and significant. Okay, very, very minor, but significant. Let's show this. The electrons flow up to oxygen now. 3 lone pairs on oxygen, negative charge, positive charge on carbon. Now, the reason it's valid because you can break bonds heterogeneously, meaning you can break them to make anions and cations. You can't just break them apart and make diradicals, but you can make a minus and a plus. It's valid, and it is a very important reactivity clue because of electronegativity. We're going to get to the reactivity much later, but oxygen is more electronegative. Electronegative atoms are going to pull electrons toward them, so therefore this is valid and significant. But it's minor, meaning this is the major by far because the octets are filled. Again, we prefer filled octets, but this is minor, yet valid and significant. Okay, it's a clue to reactivity. I want to plant some things in your mind for much later. So that's valid and significant. So let's do a few more examples to help us see. Some of these we've done. I want to give you some words to explain some of what we've already seen. Let's see some types of resonance. Okay, 1, you can have a lone pair adjacent to a multiple bond. Okay, we showed several examples of that. Lone pair adjacent to multiple bond. Okay, we showed a carbanion next to some multiple bond. We did 2 examples actually. We showed sharing a positive charge, or maybe to be consistent, we have a consistent in the language. You could say this: a positive charge adjacent to multiple bond. So you can have a lone pair next to a multiple bond. You can have an anion next to multiple bond. That's number 1. Number 2, you can have a cation next to a multiple bond. Okay, we did those. We did several examples of those. The third one is a lone pair adjacent to a plus charge. So it's kind of a combination of the other 2. Lone pair adjacent to positive charge. So let's show an example or two of those, and then we can wrap up. Okay. A couple examples are the following. Lone pair adjacent to positive charge. There's a positive charge on carbon, 3 bonds. If you calculate it, you come up with plus. Now an oxygen adjacent to or next to, these lone pairs can push in. We're going to talk about all the orbitals around these atoms to help you understand this even more, not too far from now. But these lone pairs can push in, forming an oxygen-carbon double bond and putting a formal charge on oxygen. Okay. We'll talk about this in class a little bit, but I want to make a point here. This is actually the major. It's counterintuitive based on what we just said about electronegativity, but it's going to make some sense as we talk about it more. The major contributor has the plus charge on the more electronegative atom. Okay, this is an issue. Okay, an issue in terms of understanding. Okay, the reason being is we would argue octets are filled. We have filled octets here in the major, and that's a significant issue, significant preference. And a plus charge only indicates formal charge. It doesn't mean the oxygen is going to be, that the oxygen has electropositive character. Okay, we'll see. This is another clue to reactivity. Okay, so a lot of these concepts we're just planting right now. Okay, so let's look at nitrogen. Can do the exact same thing. Adjacent to a plus charge, this pair of electrons can push in. And again, put the plus charge on the more electronegative atom for the same reason. Okay. All right, we looked at several hybrids. Just to remind you of the term delocalization, we spread out charge over more atoms when we draw resonance structures. Okay, more resonance structures means more delocalization, means more stability, and that's going to be a very, very important point. Okay, so there's examples in the book, and we'll talk about this in class as well. Very important concept, resonance. And that concludes this lecture. We'll talk about molecular structure in the following lecture.